In March 2004, the European Space Agency launched the Rosetta spacecraft on a hunt for the building blocks of life beyond Earth. Its destination was 250 million miles away and counting. A moving target hurtling through space at 37,000 miles per hour. A lump of ice and dust the size of Mount Fuji. The comet 67P. Rosetta's mission was to land on it and find out what it's made of. From 2011 onwards, Nicola Altobelli was Rosetta project scientist.
We think that comets, when they were formed, remain somewhat frozen in a state that has not changed for billions of years. So the idea is maybe they've incorporated the organic material that was already present in the molecular cloud from which the solar system evolved.
Because comets formed in the icy outer regions, they hold a frozen record of the solar system's birth. And as the young Earth cooled and oceans formed around 4 billion years ago, some of those same comets came crashing down to Earth. So could it have been comets, bearing the carbon-based organic molecules from our solar system's birth, that seeded life on Earth? It was the task of Rosetta's landing module, Philae, to find out.
In the morning, there was confirmation of the separation. The first image arrived, taken by the lander when it was separating from Rosetta. Then there were 7 hours of waiting.
Around 4 p.m. came the confirmation of touchdown. But the follow-up signals suggested something wasn't right.
The first panoramic images that were taken of the surface showed an orientation of the lander which was not as it should have been. And as the hours passed, we realized that the anchor had failed.
Philae had bounced back into space, then bounced a second time before finally coming to rest several hundred meters away.
I remember someone saying, Philae dances a little samba, but we performed most of the scientific experiments that were planned. One could even say because it bounced in several places, it allowed us to obtain data from different areas of the comet. And the orbiter perfectly fulfilled its mission.
The results were remarkable. Philae detected 16 organic molecules in just a tiny sample of dust kicked up by the initial touchdown. Among them, some of the key building blocks of life on Earth.
50% by mass of the dust particles ejected by the comet is organic, carbon-based material. This organic material came from the molecular cloud from which the solar system was formed. And thus may have seeded Earth with all this organic material. The organic molecules necessary for the emergence of life on Earth were already present in space.
Rosetta demonstrated that the building blocks of life on Earth were created during the birth of our solar system. But what about beyond? Could these same vital ingredients be part of the birth of all stars? In 2015, high on the arid mountains of the Atacama Desert, Professor Karen Oberg set out on a hunt for the building blocks of life in the birth cloud of an alien star system with the help of a new telescope called ALMA.
ALMA consists of 66 individual telescopes that's all working together. It operates at millimeter wavelengths. And millimeter wavelengths is where we can detect molecules, some of these organic molecules that we are so interested in.
Oberg turned ALMA's gaze towards the Taurus system and found the young star MWC 480 in the throes of labor. Girdled by a disk of gas and dust, from which planets were being born.
We see this dust and gas that's surrounding these young stars, and what's even more exciting, we see that they often have little lanes or tracks in them where it looks like planet formation is going on right now.
After months of collecting and analyzing the data, Oberg announced a discovery that blew the odds wide open of finding a second Genesis on other worlds. In the disk of this alien solar system, ALMA had detected some of the same organic molecules that helped give rise to life on Earth.
We found 3 kinds of cyanides, 3 molecules in the same chemical family. And those 3 kinds of molecules have also been found in our own solar system in comets.
The same organic molecules with the same miraculous potential to create life are out there among the stars.
Chemistry is awesome. It's the reason that we are alive and that we're here in the first place. So far, it's only one system apart from our solar system where we have this chemical information. But my intuition would be that it's going to be very common. This kind of chemistry is going to be almost universal.
Professor John Sutherland is trying to retrace the steps in the origins of life, in search of the processes that animate a cell into being.
Of course, the cell is more than just the chemicals that comprise it, because a cell that's just died is still the chemicals that are there. So there's something that energizes it, that coordinates it. And we don't know how to get that, but that's the goal.
So what we're doing here is putting the sample into an apparatus in which it will be irradiated by ultraviolet light.
In a series of experiments that simulated the conditions of a young rocky planet, Sutherland successfully achieved stage 1, producing the basic components of a cell: lipids, proteins, sugars, and nucleic acids.
What we found is that you can make all of the components for life under slightly different conditions. When you first see it happen, it's like magic. But it isn't magic. It's not as hard to make as we originally thought.
All the hardware of a cell can be created from a single base molecule that's widespread among the stars. But what about the next step? How is that hardware organized and energized into life?
If the conditions are the same elsewhere, what are the chances that you can go from building blocks to life? The chemistry of cells is unique in that it's self-organized. So one part of chemistry is actually controlling another, and yet somehow that's controlling the first one. Chemists are used to controlling the chemistry themselves, and the idea of letting things run and go off of their own accord is something that goes slightly against your chemical education. How can chemistry take place, if you like, with the experimenter just setting the system up and then letting it go of its own accord?
DNA is the blueprint for all of life on Earth. An instruction book for how to make and maintain all living organisms. Encoded in the twin coiling lines of a double helix is the genetic information that tells life to build a rose, or a leopard, or a blue whale. If we find DNA on other worlds, there's no doubt that there's been life there. The prehistoric organisms that built stromatolites were so successful, they ruled the Earth for up to 3 billion years. Life finds a way. And somehow these crafty architects found a way to organize water, carbon molecules, minerals, and energy into a living cell. Is this what we should be looking for on alien worlds? Around 500 million years ago, long since stromatolites first took root in the shallows, Earth's oceans bloomed with animal life. It was a very different world to the one that had made way for microbes. With air to breathe now, and a protective atmosphere under a gentler sun. Professor Peter Ward is one of the originators of the rare Earth hypothesis. The theory that the long-term habitability of Earth for animal life may be rare in the galaxy.
Habitability is really the ability of a planet to have conditions that can allow life first to originate, but secondly to stay alive. Habitable worlds can be just a short instant in time, and then it changes and it gets nasty. So what to us made Earth rare is the long-term habitability of the planet. The fact that it has remained constant in temperature, with the oxygen values we have, that we don't have these extremes in climate, that we've got this constancy, that's the rarity of it.
The great marvel and the paradox of wide open spaces is that they make us look inwards. Confronted with the infinite, we reflect upon the self. Where do we come from? Why are we here? Are we alone? Today, as Chair of Astronomy at Harvard University, Loeb is part of a generation of elite scientists riding a revolution in the quest to understand our place in the universe.
We are living at a very special time. Over the past 2 decades, thousands of planets were discovered around other stars. And we realize that our solar system is not rare. There are planets around almost every star, and moreover, about a quarter of all stars have an Earth mass planet orbiting just at the right distance for liquid water to exist on its surface and for the chemistry of life to develop.
The odds of finding life among the stars have never been better. Following the detection in 2016 of organic molecules on the moons of Saturn on the comet 67P and in the disk of an emerging star system, scientists now believe that the building blocks for simple life are common throughout the universe.
In my view, it is very likely that primitive life exists on many other planets. The question of whether intelligent life exists is more difficult to answer because we don't fully understand what led to our existence. And moreover, intelligent life existed on Earth just relatively recently in cosmological terms. But I'm agnostic about whether the answer is yes or no. I think we should explore rather than have a prejudice, just like Columbus went out to discover the new worlds. The answer lies in space.
What would it take to calculate the odds of finding intelligent life among the stars? In the early 1960s, one audacious astronomer, Frank Drake, devised an equation to answer that question. Drake listed 7 variables he believed would need to be worked out in order to determine the number of intelligent civilizations in our galaxy. With 6 of those 7 variables unknown at the time, Drake did not foresee a ready solution. R stands for the rate of star formation, or the number of sun-massed stars born each year. In 1962, Drake put the figure at 10. But it wasn't until 2011 that NASA's Kepler Space Telescope gave us the answers to the 2nd and 3rd variables in Drake's equation: the fraction of stars that have planets, and the number of those planets with the right conditions for life to form.
It turns out that the fraction of stars with planets is approximately 1. Every star you see in the sky, when you walk out at night and look at a random star in the sky, it has a planet, at least 1. And then the number of planets in the habitable zone turns out to be, on the order of 0.2, okay? So this is like saying, if you look at between 4 and 5 stars, one of those is going to have a planet in the right place for life to form. Remember that the galaxy contains 400 billion stars, just the galaxy alone. 400 billion stars, right? So when you think about all those stars in the galaxy, that's an amazing number.
Up to 80 billion exoplanets in our galaxy have the right conditions for life. When you consider that at the time Drake formulated his equation, no one knew if there was even one exoplanet out there, this truly is a revolution of our understanding. But what about the other unknowns in the Drake equation? Inspired by Kepler's game-changing discoveries, a new generation of scientists has made it their mission to fill in the blanks. Of all the habitable exoplanets out there, how many of them actually host life? This is the next unknown in the Drake equation, and the challenge it presents for scientists is immense. How does one detect life from light years away? One approach that shows promise is to study the gases around exoplanets in search of a so-called biosignature, the evidence of life imprinted in the atmosphere.
I think one of the things that's most exciting for exoplanet atmospheres right now is that we can actually measure gases with telescopes from Earth. Remote sensing is a very powerful technique. It's how we first studied the solar system.
Planetary scientist Sarah Horst is a leading investigator of atmospheric chemistry, a field that took off in a radical new direction in 2001 with the first ever detection of an exoplanet's atmosphere. While atmospheric observations so far have been limited to a narrow range of gases, the James Webb Space Telescope will be the first instrument capable of sampling a broad spectrum. The challenge now for researchers like Horst is to define a set of biosignatures, gases that indicate the presence of life, for the James Webb to go looking for. Horst's generation may well be the first to put a number on the fraction of habitable exoplanets that host life. But the next unknown in the Drake equation could prove much more challenging to resolve. How many of those life-bearing planets go on to develop intelligence?
Even if we understand that other planets have simple life on them, and indeed we might be able to make astronomical observations to test that in the next 10 or 20 years, then of course there's another big uncertainty, which is how likely it is that simple life evolves, as it did on Earth, into a marvelous complex biosphere containing even creatures like ourselves. We don't know what the chances are of getting from simple life to advanced life of the kind we recognize as intelligence.
The fourth variable in the Drake equation, the fraction of life-bearing worlds that evolve intelligence, still eludes scientists today. On Earth, the great burst of life during the Cambrian explosion was an integral step on the path to intelligence. But could widespread death have been just as important? If our own existence is the outcome of a random cosmic disaster, then might the fraction of worlds that evolve intelligence be equally unpredictable? But if we could go looking for alien intelligence on another planet, how would we recognize it? Professor Roger Hanlon is an expert on the closest thing to alien intelligence on Earth: cephalopods, squid, octopus, and cuttlefish. The undisputed masters of disguise, because they have to be.
Cephalopods are soft-bodied. All their armor was given away through evolutionary time to their cousins, the oysters and the clams, and they are soft-bodied. They're extremely vulnerable. So they have to get on by their wits. They have to do something different. They're making that decision in far less than 1 second. In about 1/3 of 1 second, they're assessing that visual scene. Now they're orchestrating in their skin 30 million chromatophore pigment organs in the skin that create the pattern, and iridescent reflective cells, and even the skin papillae and the bumps. There are several thousand of those. So that takes a lot of cognitive processing, a lot of brain power.
Cephalopods have the highest brain-to-body mass ratio of all invertebrates, and their brains are decentralized, throughout their body. Since the 1960s, when Frank Drake drafted his equation, the search for extraterrestrial intelligence has been defined in terms of the search for a technological civilization. Being unable to travel to the stars, Drake's solution was to scan for signals that our Earth-bound technology could detect. Hence the penultimate unknown in his equation: the fraction of intelligent civilizations that develops technology. The new technology when the Drake equation was formulated was the radio telescope, and those who search for extraterrestrial life today still believe an alien radio signal is what we're most likely to detect. Seth Shostak has spent his life listening to the stars.
Okay, thank you.
As senior astronomer at the Institute for the Search for Extraterrestrial Intelligence, or SETI, it's his job to scan the heavens for alien technology.
We try anything we can to pick up some information, some sort of signal that would tell us, we don't know what they're like or what their taste in music is or anything like that, but what we do know is that they're smart enough to build a radio transmitter, for example.
With limitations on technology, time, and resources, the dilemma for SETI has always been where to listen.
We haven't heard anything. Let's be straight up about that. And some people think, the reason you haven't found anything is because there's nothing to find. we're the smartest things in the universe. Well, I don't think it's true. I think the reason that we haven't heard anything is simply because we have only looked at a very small number of star systems. But that's changing because of the improvements in technology. Instead of looking at a couple of hundred star systems every year, we'll be able to look at a couple of thousand, and then 5 years down the road, it'll be tens of thousands. And in the next 24 years, we'll be able to look at on the order of 1 million star systems. Now, if you look at 1 million star systems, the chances of finding something are not so small. So I bet everybody a cup of coffee will find ET within 24 years. I could be out a lot of coffee.
For almost 50 years since Drake wrote his equation, we listened. But nothing we heard couldn't be explained as interference or a natural phenomenon. Until one day in 2007 in rural Australia, astronomers picked up the first in a series of mysterious signals that still puzzle the science community today.
At first, we didn't dare believe they were real. Fortunately, I've seen them with my own eyes. I saw the very first sweep of the first one. Couldn't sleep that night. I was like, could this possibly be real? This is amazing. And we've been able to work out how far away they are in the universe, and they're impossibly far away. They're billions of light years away. So the process that creates them is so energetic that it's a great mystery as to what causes them.
The strange signals have been dubbed fast radio bursts, blasts of radiation so powerful they emit the energy of 500 million suns. Professor Matthew Bales leads an international effort to study the phenomenon here at the Molonglo Observatory.
Fast radio bursts are these mysterious bursts of radiation that only happen for a few milliseconds. The sky lights up and then they go away again. They're about 1 million times more luminous than anything we've known about in our own galaxy.
Since the first detection in 2007, there have been more than 40 fast radio bursts detected worldwide. 5 in just the last year were detected here by Bales.
One of the holy grails is to find a repeating fast radio burst. And is there any pattern to the fast radio bursts? Do they come in special gaps, or are they regular? If they're very regular, we might associate that with a rotating neutron star where a sort of death ray is going past the Earth, once every 20 seconds or something. If they come at irregular intervals, or if they came separated by a code that showed us that there was some higher intelligence behind it, you might think there's an intelligent civilization that's actually transmitting this signal. That would be Nobel Prize winning stuff.
Of course, the next question then is, could we or should we send a message back?
If we took our biggest radio telescope, we could actually mimic what a fast radio burst would look like. And if we were trying to communicate with other intelligent beings, we might imagine that they go through a stage of their evolution where they're searching for fast radio bursts in the same way I am here. And then if you could find one that repeats and find a pattern, that might be a way of doing inter-civilization communications, which is a fascinating thing.
What we're really interested in is a civilization like ours. An industrial civilization that shows signs that in building tools, of whatever kind, they have gotten to the point where they clearly have a kind of reasoning, rational intelligence, a culture that we might be able to talk to them, right? Because that's really what we want to know. We want to know, what's it like to be them? Because all we know is what's it like to be us.
If I received a signal from outer space, how could I tell it was a language, as opposed to anything else?
To put a figure on the fraction of civilizations that develops communication, we need a way to decipher if an alien signal is actually trying to tell us anything.
I analysed over 60 different languages, human languages, plus languages like dolphin, chimp, the bird song. So on the left here, you've got Neil Armstrong speaking from the moon. On the right here, you've got a dolphin communicating. You can see here quite easily the rhythms going on, sounds that we're making, how similar those constructs are. It's picking up those rhythms and those interrelationship patterns that I think are fundamental to any communication, whether it's on this planet or in another planet. And looking at the complexity of how those patterns interrelate, you can actually tell how intelligent the author is.
When a signal arrives, it's first checked against known sources of interference. Algorithms then scan for the telltale patterns of communication, whether its source may be an audio recording or an intergalactic email.
It's an awfully big sky. We're getting more and more capability online, the hardware to do it. But I suspect, unless we eavesdrop on something, it may be a while before we hear anything. We want to be ready for it. So there's no point just sitting back and thinking, well, we'll do something when it happens. It's doing all this ahead of time so we're prepared for it. But again, it could happen tomorrow. We just don't know.
Recent advances in the remote observation of planetary atmospheres have opened up a new method of determining whether an exoplanet hosts or has previously hosted a technological civilization.
The composition of the atmosphere can provide us with a hint about the intelligent or perhaps not so intelligent life that pollutes the atmosphere with industrially produced molecules.
Pollutants such as chlorofluorocarbons are released into Earth's atmosphere by industrial processes and do not occur naturally. Detecting them in an alien atmosphere would therefore be a clear footprint of technological life.
Some of these molecules exist for tens of thousands of years after they were introduced to the atmosphere. So in principle, we can find evidence for a civilization that is no longer in existence on the surface of that planet. We can find graveyards of other civilizations.
The question is, how long are we going to last? Do we only have another 200 years before we collapse? Do we have, 200 million years in front of us? So this is, it's really a fundamental question. And it's a fundamental question for human beings, because right now with climate change and sustainability, we really face this existential crisis about really, are we going to be able to make it through to more than another 100 or 200 years?
Could this be the ultimate limiting factor in the Drake equation? That before technological civilizations work out how to search for life among the stars, they destroy themselves.
In order to become truly a spacefaring race, that takes a lot of time. To be able to really have settlements on Mars, to really start to begin to have a human presence in the solar system, will take hundreds of years. And, if we can't make it more than a couple hundred years, clearly we're not going to develop that kind of society. And then to ever really think about getting to the stars, sending probes to the stars, being around for the signals to come back, you have to last a long time. I think those two things are intimately connected, and you don't get the stars